So today I'll be presenting on a couple different things from two different papers, starting with stuff about the Q value and a related statistic, the pi zero statistic, and then also talking about just how to compare differential expression results across different data sets, which is something that we were asked to do differently on a recent review. So I'll start from this statistical paper from John Story and Robert Tibshirani. And it's all about the Q value, which some of us have used. Basically, there's a few different related concepts in this paper. Of course, we can start with the P value. Obviously, we all use this every day. But I think maybe the exact definitions can be easily confused. So the p-value really tells us about the false positive rate. So a p-value of like 0.01 would mean that like if you take all truly null tests, 1% of them will be called significant even though they're actually null. In other words, like if we're asking if genes are differentially expressed, 1% of the ones that are 1% of genes will be, or I guess it's 1% of null tests are called significant. So that's not really telling us about a related concept called related to FDR. So FDR would be, instead of talking about false positive rate, it's a false discovery rate. So we're not talking about the truly null tests. It's more about like, if we take all the significant results, how many of those are truly null? So that's, the p-value doesn't directly tell us that. So really, FDR is something that's more important to care about because we care about controlling. When we're making statements about certain results, we want those statements to be true. So FDR gives us direct control over that. So the Q value is related. And the exact definition for a particular feature may be a little counterintuitive. So it's like, for a particular feature, it's the proportion of all significant tests expected to be null when you call that feature significant. So it's really making a statement about all the tests you're doing. So if you're testing differential expression for multiple genes, it's talking about that proportion over the entire set of tests. So while the definition for a particular feature might be maybe like slightly counterintuitive, setting a threshold for the Q value gives us a really interpretable statistic, which is like, for example, if you set a threshold of 0.05 for Q values and you take all results that are all features that pass that cutoff, then you get basically you expect 5% FDR. So 5% of significant results are actually null. So setting a Q value threshold gives you sort of like direct control over the FDR, and that gives you a really interpretable way to control false positives. Now there's another statistic in this paper called the pi zero statistic that they also present in the Q value paper. So this is really the estimate. It gives you an estimate of the proportion of tests that are truly null. So if you're testing genes, like I've been talking about, it gives you an estimate over like how many genes you actually expect to be differentially expressed or not differentially expressed. So they give this definition, like a mathematical formula for it. It's essentially counting p-values, the fraction of p-values above a certain cutoff. It's a hyperparameter called lambda. Yeah, you can choose what value of lambda there is, but in the bioconductor package, which I'll cover in a second, it borrows estimates of statistic across multiple lambda values and actually automatically can give you a value for the pi zero statistic. But yeah, so while it gives you a proportion of tests that are null versus alternative, you don't actually know which genes or which features those are. So you're not able to just say like these ones are definitely truly significant versus not. But still a pretty useful measure to have. So yeah, there's a corresponding bioconductor package called Q-value. And so calculating Q-values from a set of P-values you already have is really simple. You just use this Q-value function, and it returns this Q-value, this Q object. If you do a summary of it, it gives you a bunch of different statistics. It gives you the number of significant features below certain stringency cutoffs for both p-value and q-value. It also gives you an estimate of this pi-zero statistic at the top. So in this case, like 66% of tests are expected to be null. And so you can extract that particular statistic from the object as well. So a pretty straightforward usage of this package, and then you get the pi-zero statistic as well. And so I guess moving on to the second paper in this topic. So this is more about, this is a paper about sex differences in the context of schizophrenia. So some background in this paper is that basically they have like two different cohorts, and they have hundreds of females and males. And they're doing a bunch of different analyses. They're doing differential expression within like the cohorts separately. They also merge the cohorts and then do differential expression on the entire data set. And then they also do comparisons across. So it's like within, combined, and then across. And so importantly, when they're doing comparisons across the cohorts, they're not using hard cutoffs for the p-value or FDR or q-value. So we got a recent review on a paper, and the reviewers made a comment that like it's not advisable to do this, because if you're using hard thresholds, well, the exact set of DEGs that you end up with are sensitive to the power you have on that specific data set, and that obviously varies across data sets. So you don't want a sort of a metric that's sensitive to something that's data set specific. And so I'll get into how they exactly did these comparisons, mostly focusing across, like on the differences across cohorts, though this paper covered more than just that. So one of the things they did was this is talking about case control T statistics. So they have one cohort on the x-axis and the other on the y-axis, and they're taking the case control T statistics and just doing a scatter plot of those. And then they're reporting two associated metrics. They're reporting the Spearman correlation of all the points, which is very high in this case, and the p-value associated with the correlation, which of course is very low with this amount of data. And so they do report like sort of top genes, but they're not using hard cutoffs. So of course you see like the corners, the top right and the bottom left are where the magnitude of the T statistic is high in both data sets, but they're not sort of drawing a vertical or horizontal line, which would indicate that you're using a hard cutoff on one of the data sets. So they make actually a bunch of these comparisons, one of them for case control, one of them for sex differences, and then they do a third one. I forget exactly what they're doing, but this is like a common way that they're using to compare differential expression results across two different cohorts. And then I mentioned that they also combine, they're taking the cohorts, they're just putting it into one big data set, and then they're doing case control differential expression. So that's a way to like capture schizophrenia related signal that's shared among the data sets without explicitly trying to ask which is in which data set. So of course, the common way to do that is with volcano plots. So this is part of their figure 1. And then they explore of course, the genes that pop out with the highest significance, and then log fold change as well. So that's all I had for this paper. There's a lot more to this paper, but I was focusing mostly on the comparison across cohorts, and so that's something that recently came up for us when comparing data sets across brain regions.
The concordance is between the two lists from that you get from differential expression list of genes. They are sorted by or genes or whatever features you are getting from the like a top table output, for example, from Lima. You get this list of features, and you have them sorted by p-value, and the concordance is this cumulative proportion of shared names of the features, shared IDs, that you calculate for each rank. Rank meaning the order of that name in the list, right? So the way it's done, if you go by this at the top, I have this actual real example for the plot above. So the rank is just the order of genes in the list with the lowest. The first rank is the lowest p-value, and then as you for x-axis you have rank, which is if you have for number one, how many of these top one genes overlap, top k. So we increase the k here, 1, 2, 3, the rank. And in this case, in this example, we have the top are actually identical. So I mark this with the green links here. I'm showing the common ensemble gene IDs. So that's why that's a proportion that forms for each rank. This is what you plot. The concordance is this value percentage, the proportion of how many of these are shared as you increase the rank in these lists. So that's what I'm showing here, this proportion. That's why you see of course, the list at the beginning is very unstable, and then it kind of becomes, as you go up, the numbers becomes more linear, the more continuous and smooth the curve. This is zoomed in to only show in the top 50 ranks, top 50 genes in each data set. So usually you look at the top 1,000. So that's why, like I showed in the summary slides there, when we use it in a larger context, when I have this GG pairs visualization, this concordance at the top, we usually look at, we decided like 3,000 genes to show how this goes. And I also have the proportion, so the proportion at the end is this number here, 34 in this case, but we also have this 350. I put an arbitrary number of rank 350, as I noticed that in around that range, it's kind of stabilizes the curve, the plot, and we also show this proportion here.
So that 350. Like ideally, if you have some external information about like what number of genes you expect to be differentially expressed in what you're studying, that should be like what the point that you're looking at, right? I guess you could maybe use the pi0 to try to inform that decision. The dotted line that you see there, like diagonal line, is just the expected matches at random.
Yeah, this
and so you can see that at some point the black, full line basically becomes parallel to the expected at random line. So like you're just adding random information at that point. At the very beginning, like between 0 and 25, the curve is very unstable of the concordance at the top. So we saw that later. These methods actually were first implemented by Rafael Irizarry. He has a paper where he's like, well, it doesn't show, I think, 0 to 25 or 0 to some small number, because the concordance at the top is not stable at that point. Then it becomes stable, and like for the work he was doing, he had an idea like what was the number of differential expressions to expect. Yeah, so I think like the plotting function here that Geo has made could be quite useful for these threshold-free comparisons. I think we could like improve it a little bit by like putting the p-value of the Spearman rank correlation on the bottom left triangle. So like on those scatter plots. And like I guess you could have an option of saying like instead of 350, maybe try to guide that decision by like the pi0 statistic from the Q-value package. But yes, in this particular data set, it's true that like if you focus on the first row, second column, like it does look like after 350, like you only have stuff that is random. But before it, the curve is not following it's not parallel to the random line. In other cases, like maybe 350 is too far out on the x-axis, like that second row, fourth column one that like Gio was pointing at, fourth column.
Yeah, these two.
Fourth column, second row.